Okay, let's unpack this. Think about the computers we use every day. They've gone from massive machines filling entire rooms to devices so powerful they fit in our pockets, enabling everything from instant global communication to complex simulations.
Yeah, it's pretty incredible.
It's an astonishing trajectory powered by relentless innovation.
Absolutely. And a key driver of that innovation has been, well, the ability to make components smaller and smaller.
Right.
This trend is often summarized by Moore's law, which, while not a strict physical law, has been a remarkably accurate observation that processing power doubles roughly every 18 months, largely because we can cram more transistors onto a chip.
And you can see the shrinking trend visually. Our source includes a figure 1, that shows how the number of atoms or dopant impurities needed to represent a single bit of information in computation has been dropping dramatically since the 1950s.
It really has.
The curve is steep, and it suggests we're rapidly approaching a fundamental boundary, the atomic scale itself.
Exactly. And this is where classical computing starts to hit a wall. Because when you get down to the size of individual atoms or electrons, the rules of classical physics.
The everyday physics we're used to?
Yeah, the physics of levers and gears and electrical switches that governs our current computers, those rules simply don't apply anymore. At that scale, matter behaves according to the bizarre and counterintuitive rules of quantum mechanics.
So it's not just about physical size limitations. Even if we could build components atom by atom, classical computers face another kind of bottleneck, don't they? Their fundamental nature.
That's right. Classical computers, at their core, are serial machines. They process information step by step, one calculation after another.
One thing at a time.
Pretty much. Even systems we call parallel computing are essentially just breaking a large problem into many smaller serial tasks and running them simultaneously on different processors. But the underlying logic, based on bits that are definitively 0 or 1, remains serial.
And that limits them.
It fundamentally limits their ability to tackle certain types of problems efficiently. Some problems just get exponentially harder.
And here's the aha moment this deep dive is all about. Quantum mechanics isn't just a problem that stops us from making classical computers smaller. It's potentially the solution. It provides the foundation for an entirely new way to compute.
That's the core insight. The very strange behavior of particles at the atomic level, governed by quantum mechanics, can be harnessed to build computers that operate on entirely different principles.
Computers that aren't stuck with those classical limits.
Exactly. Computers that aren't limited by the classical bottlenecks of serial processing or the constraints of classical physics at tiny scales. They can solve problems that are simply impossible for even the most powerful supercomputers we have today.
Okay, so this revolutionary idea didn't just appear out of nowhere. Who are the early thinkers who dared to imagine computing at the quantum level?
Well, the seeds were sown back in the 1970s and early 1980s. We're talking about pioneers like Charles H. Bennett, Paul A. Benioff, David Deutsch, and famously Richard P. Feynman.
Right, Feynman.
They were looking at the relationship between computation and physics, realizing that the fundamental limits of computing might actually be physical limits.
And Feynman, with his unique intuition, seemed to grasp something particularly important about quantum systems and computation.
He did. In 1982, Feynman proposed that you could use a quantum system itself as a computer. His key insight was that simulating other quantum systems on a classical computer is incredibly inefficient.
It just bogs down.
Totally. As the number of quantum particles you want to simulate increases, the computational resources needed on a classical machine grow exponentially. He suggested a quantum computer, however, could potentially simulate such systems in polynomial time.
Okay, exponential versus polynomial, that's a huge difference.
It's a difference so vast, it's like comparing walking across the country to flying. It's night and day.
Which makes intuitive sense if the universe at its most fundamental level is quantum mechanical. Maybe the best tool to understand and simulate it is a quantum computer.
Precisely. Then, in 1985, David Deutsch took this further. He proved that, in principle, any physical process could be perfectly modeled by a universal quantum computer.
Any physical process. Wow.
Yeah, this hinted at a computational power far beyond anything classical machines could ever achieve. It opened up the possibility space enormously.
But it was a specific breakthrough, an algorithm, that really moved quantum computing from an interesting theoretical concept to something with potential world-changing implications, wasn't it?
Absolutely. That was Peter Shor's algorithm in 1994. Shor developed a quantum algorithm that could factorize very large numbers exponentially faster than any known classical algorithm.
Okay, why is factoring large numbers such a big deal? My calculator can do that.
Well, your calculator can factor small numbers. We're talking very large numbers, numbers hundreds or even thousands of digits long.
Ah,
Factoring those is the mathematical problem that provides the security foundation for most modern public key cryptography. Think RSA, the algorithm that secures online transactions, email, and so much of the digital world we live in.
how does that work?
The security relies on the fact that, well, it's computationally easy to multiply two large prime numbers together.
Yeah, computers are great at multiplying.
It's extraordinarily difficult and time-consuming for classical computers to do the reverse.
Yeah.
Take that enormous product and find the original prime factors.
And the source gives some striking examples of just how hard this is classically.
It does. It mentions the factoring of RSA 129, a 129-digit number, back in 1994. It took 1,600 workstations working together for about 8 months.
8 months with 1,600 computers.
Yep. And based on that effort, the source points out that using the same level of classical computing power, factoring a 250-digit number is estimated to take around 800,000 years.
800,000 years.
And a 1,000-digit number, an estimated 10 to the power of 25 years. That's a number far, far larger than the estimated age of the universe.
That's practically impossible then for classical computers.
Essentially, yes. It's considered computationally intractable.
So Shor's algorithm, running on a sufficiently powerful quantum computer, could potentially break the encryption that protects the internet today. That's a massive implication and explains why governments and companies suddenly took notice.
Exactly. It demonstrated a concrete problem of global importance, where quantum computers offer not just a speed-up, but a qualitative leap, an exponential advantage over the best classical methods.
Yeah, that definitely changes things.
It changed the perception of quantum computing from pure science to a potential technological revolution with geopolitical consequences. Suddenly, it wasn't just theory anymore.
And factoring isn't the only problem where quantum computers offer a dramatic speed-up.
No, it's not. Another famous example is Grover's algorithm, developed in 1996. It provides a quantum speed-up for searching unstructured databases.
Like finding a needle in a haystack.
Sort of. If you're looking for a specific item with a desired property among n items, a classical computer, on average, might need to check about n2 items.
Okay, check half of them, roughly.
Grover's algorithm can find the item in approximately the square root of n operations.
Square root of n. So for a million items.
For a million items, that's the difference between checking roughly 500,000 items classically and just 1,000 items quantum mechanically.
Still a big improvement.
Still a significant speed-up,
Right.
though not exponential like Shor's, but very useful for certain search problems.
So to recap Act 1, classical computers are hitting physical limits as components shrink and face fundamental limitations due to their serial nature and reliance on classical physics.
Hitting the wall.
Quantum computing, born from grappling with the bizarre rules of the atomic world, offers a potential way around these limits by harnessing those very rules.
Using the weirdness to our advantage.
Promising exponential speedups for certain critical problems like factoring, which has huge implications for cryptography.
It's a shift from trying to build ever faster classical machines to building a fundamentally different kind of machine based on physics that baffled even Einstein.
All right, let's dive deeper into how this is even possible. What's the fundamental building block of quantum information replacing the classical bit?
That would be the qubit, or quantum bit.
Yeah.
Classical bit is straightforward. It's either a 0 or a 1, always one or the other, fixed.
Black or white?
Exactly. A qubit is where things get interesting because of quantum superposition.
Superposition. That's the idea that a quantum system can be in multiple states at once, like being 0 and 1 simultaneously.
Precisely. Unlike a classical bit, a qubit isn't restricted to being just 0 or just 1. It can be 0, 1, or a combination or superposition of both states simultaneously.
The spinning coin analogy comes up here, right?
It's a good one.
Yeah.
Think of that spinning coin. Before it lands, it's in a state that represents both heads and tails simultaneously. Only when it stops.
When you measure it.
Right, when you measure it, does it collapse into a single definite outcome, either heads or tails. A qubit behaves similarly until you measure it, at which point it collapses to either 0 or 1 with certain probabilities.
So mathematically, how do we describe this both at once state? It's not just 50-50, is it?
No, it's more nuanced. The state of a qubit is represented as a vector in a two-dimensional complex space. It's written as a linear combination, basically a weighted sum of the classical basis states, which we write as 0 and 1.
Those are the standard quantum notations.
Yes, and the weights are complex numbers called amplitudes. These amplitudes tell you the probability of measuring the qubit as a 0 or a 1 if you were to observe it. The key is that before measurement, it exists as this combination, this superposition.
What physical systems can actually embody a qubit? What can we use as that spinning coin?
Well, our source mentions a couple of common examples. The spin of a single electron, for instance, can be either spin up or spin down. We can map one to 0 and the other to 1. Similarly, the polarization of a single photon, whether it's horizontally or vertically polarized, can represent the two states.
And these tiny systems can actually be put into these superposition states.
Under the right conditions, yes. They can exist in a blend of, say, spin up and spin down simultaneously.
And we can see evidence of this superposition in experiments, like the beam splitter experiment described in the source. That sounds fundamental.
Yes, it's a classic way to demonstrate single particle interference, which is a direct consequence of superposition. Look at Figure 2 in the source material. Imagine sending a single photon towards a half-silvered mirror, a beam splitter.
Okay, like a mirror that lets half the light through and reflects the other half.
Exactly. Classically, you'd expect it to either reflect off the mirror or pass straight through it. If you have detectors on the other side, say detector A and detector B, you'd expect the photon to arrive at either A or B, but never both.
Seems logical it took one path or the other.
But quantum mechanics says something different happens. It says the photon doesn't just pick one path. It enters a superposition of taking both paths simultaneously.
How?
It's on the reflected path, A and D, the transmitted path, at the same time. Its wave function, the mathematical description of its state, splits and follows both routes until it interacts with something like a detector, at which point the superposition collapses.
Figure 3 takes this further, showing how the paths can be recombined.
Right. If you use fully silvered mirrors to redirect both potential paths back together and then send them through another beam splitter, you can observe interference.
Like waves interfering.
Exactly like waves. If the path lengths are precisely equal, you'll find something amazing. The photon is detected at detector A 100% of the time and never at detector B.
Never at B. But why?
Even though it's a single photon, the parts of its wave function that took each path interfered with each other when they recombined. They interfered constructively towards detector A and destructively towards detector B, canceling out the possibility of arriving at B.
Wow. And the spooky observation mentioned is that if you block just one of the paths,
Then everything changes.
the interference disappears, and the photon can now arrive at detector B with 50-50 probability between A and B.
Precisely. The photon seems to know if the other path is open. If both paths are available, it interferes with itself in a way that prevents it from going to B.
But if one path is blocked,
It behaves like a simple particle or wave that just traveled that one available path, with probability splitting normally at the final beam splitter. This strongly implies the single photon was, in fact, in a superposition of being on both paths simultaneously before they were recombined.
so superposition is key. A qubit can represent multiple states at once. How does that translate into computational power? This feels like the core.
This is where the concept of quantum parallelism comes in, because a system of multiple qubits can be in a superposition of a vast number of possible classical states all at once.
How many?
For example, a system of n-qubits can be in a superposition of 2 to the power of n classical states, 0, 0, 0, 0 via 1, 0, 10, and so on, all simultaneously.
That number grows incredibly fast.
It does. 2 qubits can represent 4 states, 3 qubits 8, 10 qubits over 1,000, 30 qubits over 1 billion.
Okay, so a quantum computer can hold all these states at once. Then what?
It can potentially perform an operation on all those 2n states simultaneously with a single step. The source calls this parallelism on a serial machine, because the computation is happening within the single evolving quantum state.
So instead of doing one calculation then the next, like a classical computer.
It's exploring a huge possibility space inherent in its quantum state all at once. That's the potential source of the massive speedup.
Okay, superposition gives us this incredible potential for simultaneous exploration. But there's another, perhaps even stranger, quantum phenomenon that's absolutely essential: entanglement.
Entanglement, yes. This is the quantum correlation that Einstein famously found so unsettling, describing it as spooky action at a distance.
Spooky action.
It's a connection between quantum particles that goes far beyond classical correlation.
Yeah.
It's much weirder.
The source uses a great analogy to explain classical correlation, Mr. Bertelmann's socks. Can you walk us through that?
Right. Imagine Mr. Bertelsmann always wears two socks of different colors, but always from specific pairs, say. He has red and green socks, or yellow and blue socks. If you see a red sock on one foot,
You instantly know the other must be green.
exactly, that's a correlation.
Yeah.
But the crucial point is the colors were determined the moment he picked the socks and put them on. Seeing one just gives you information about a pre-existing state. The outcome was already fixed.
Now contrast that with quantum entanglement. How is it different?
With entanglement, the properties aren't predetermined in the same way. The source gives an example of two atomic nuclei that are in a superposition state of decayed and not decayed. If they are entangled, they might be in a combined state where they are both in that decayed, not decayed superposition.
So neither has definitively decayed or not decayed yet.
Correct. But their fates are linked. Measuring one and finding it has decayed instantly means the other one must also have decayed, or vice versa, depending on the specific entangled state. Their outcomes are correlated, but the outcome itself wasn't fixed until the measurement.
And the E-Pura paradox highlighted this.
Yes, formulated by Einstein, Podolsky, and Rosen in 1935. They used entangled particle properties, like the spins of two electrons from a decayed system, like the one shown in Figure 4.
Like two electrons from a helium atom that flies apart.
Yes. The two electrons start in an entangled state with opposite spins antiparallel. When they separate even to vast distances, light years apart theoretically,
They stay connected.
they remain linked in this quantum way. If you measure the spin of one electron along a specific axis and find it spin up, you instantly know that the other electron's spin, measured along the same axis, must be spin down.
Instantly, regardless of distance.
That's the Suki part.
And this troubled Einstein because that instantaneous correlation seemed to imply information was traveling faster than the speed of light, violating relativity.
Exactly. It seemed like a paradox. He thought quantum mechanics must be incomplete, that there had to be some hidden variables determining the outcomes in advance, like Bertelsmann's socks.
But later work, particularly by John Bell, provided a way to test this, didn't it? To see if hidden variables could explain it.
Yes, Bell's theorem and Bell inequalities were revolutionary. Bell derived mathematical inequalities that any theory based on local realism must satisfy.
Local realism, meaning effects have local causes, no faster-than-light influence, and particles have definite properties before measurement.
Precisely. The source describes a conceptual experiment, like in Figure 5, involving entangled photons sent to polarizers set at different angles. You measure the correlations between the outcomes. Local realistic theories predict the correlation measurements would be bounded by Bell's inequalities of values between -2 and +2, basically.
But quantum mechanics predicts a value outside that range.
Correct. Quantum mechanics predicts a value about 2.8 in certain setups, which clearly violates the Bell inequality.
An experiment.
Crucially, numerous experiments over decades, with increasing precision, have confirmed the quantum mechanical prediction. They've consistently shown correlations stronger than any local realistic model can explain.
So the universe is genuinely non-local, or non-realistic, or both.
It strongly suggests that you can't have both locality and realism in the way Einstein hoped. Entanglement appears to be a real, non-local quantum phenomenon. The connection is real.
So entangled qubits aren't just classically correlated. They share a deeper, instantaneous connection regardless of distance. This spooky action is a vital resource for quantum computing.
It's absolutely fundamental. Entanglement allows for correlations and coordinated operations between qubits that enable complex quantum algorithms and information processing tasks impossible with classical bits. It's a key ingredient.
Building on entanglement, the source discusses another concept that sounds purely sci-fi: quantum teleportation. Not like Star Trek, I assume.
No, definitely not beam me up, Scotty. It's not teleporting matter. In science fiction, teleportation usually means scanning an object, destroying it here, and recreating a perfect replica elsewhere by sending all the scanned information.
And the source explains why you can't do that classically with a quantum system. Why not?
This is tied to the Heisenberg uncertainty principle and the nature of quantum measurement. To make a perfect copy, you need to get all the information about the original object's quantum state.
But measuring disturbs it, right?
Exactly. Measuring a quantum system to get information fundamentally disturbs that system. The more precisely you try to measure one property, like position, the less precisely you can know a complementary property, like momentum. You simply cannot get a complete scan of an unknown quantum state without irrevocably changing or destroying the original state.
And even if you could, you wouldn't have enough info.
Right, you don't obtain enough information to build a perfect copy classically. This is also related to the no-cloning theorem in quantum mechanics. You can't perfectly clone an arbitrary unknown quantum state.
So classical perfect cloning is impossible because you can't scan without destroying and you can't get full info. But quantum teleportation is possible. How?
Yes, quantum teleportation is possible, but it's the teleportation of an unknown quantum state, not physical matter. It's a clever process, first described by Charles H. Bennett and colleagues, based on earlier ideas by Stephen Weisner. It allows you to transfer the state of a qubit from one party, let's call her Alice, to another, Bob, using entanglement as a resource.
Okay, so Alice wants to send an unknown quantum state to Bob. What do they need?
As shown conceptually in Figure 7, Alice has her qubit in the unknown state that she wants to send. The crucial prerequisite is that Alice and Bob must already share an entangled pair of qubits. Alice holds one qubit of the entangled pair, and Bob holds the other, maybe prepared beforehand and separated.
Okay, Alice has her unknown qubit, ND, her half of the entangled pair. Bob has his half. What happens next?
Alice performs a specific type of joint measurement on the two qubits she possesses, her unknown qubit and her part of the entangled pair. This is called a Bell state measurement.
And what does that measurement tell her?
The outcome of this measurement is classical information, typically one of 4 possible results. Importantly, this measurement process destroys the original unknown state at Alice's location and also breaks the entanglement between her qubit and Bob's.
So the original is gone, but she gets classical information.
That's right. She gets one of 4 classical results. She then sends this classical information to Bob through a standard communication channel, like a phone call, email, laser pulse, whatever.
And sending that classical information is limited by the speed of light, of course.
Exactly. This is the key point. Quantum teleportation doesn't allow for faster-than-light communication because Bob has to wait for Alice's classical message.
Okay, Bob gets the message. It tells him which of the 4 results Alice got. What does he do?
Based on which of the 4 results Alice communicated, Bob knows precisely which specific quantum transformation. A simple unitary operation like flipping the qubit or applying a phase shift, represented by Pauli matrices. He needs to apply to his qubit the one that was originally entangled with Alice's.
He performs an operation on his qubit based on Alice's message.
Yes. And after Bob applies the correct transformation. Voila.
His qubit is now in the exact state that Alice originally wanted to send.
Precisely. The unknown quantum state has been effectively transferred or teleported from Alice's location to Bob's location, without any particle carrying that state physically traveling between them. The entanglement acted as the quantum channel, and the classical communication provided the key to reconstruct the state at Bob's end.
That's still pretty amazing. It's an incredibly powerful capability for quantum communication and potentially building quantum networks, right?
It is. It allows us to move quantum information reliably from one place to another, which is essential for many quantum technologies.
Okay, shifting gears a bit, the source touches on something not usually associated with computation, thermodynamics. We know classical computers generate a lot of heat. Is that just an engineering problem or something more fundamental?
It's partly fundamental. Physical processes generate heat. That's just physics. But in classical computation, erasing information is an inherently irreversible step.
Irreversible?
Meaning you can't run the process backward easily. The source mentions Landauer's principle, formulated by Rolf Landauer. It establishes a minimum amount of heat that must be generated whenever you erase a single bit of information.
There's a fundamental cost to forgetting.
Essentially, yes.
Yeah.
It's a minimum energy dissipation, ASK log 2, per erased bit, linked to the increase in entropy. So every time a classical computer throws away intermediate information it no longer needs during a calculation, it must generate at least this much heat.
Okay, that's classical computing. What about quantum?
Now, a fascinating aspect of quantum mechanics is that its fundamental operations, described by unitary transformations, are mathematically reversible.
Reversible, you can run them backwards.
In principle, yes. If a quantum computer could perform its computational steps using only reversible gates without erasing intermediate information, it could theoretically avoid the heat generation associated with information erasure during those specific computational steps.
The source mentions Toffoli gates as an example of reversible gates.
Yes, the Toffoli gate is a well-known example of a universal, reversible classical logic gate that can be implemented quantum mechanically. Reversible gates preserve all the input information, carrying it forward in a way that you could, in principle, reverse the entire computation and get back your original input.
Why is reversibility useful for computation, besides heat?
Well, this reversibility is also why quantum computers are theoretically thought to be good at handling problems considered NP in complexity theory problems, where verifying a potential solution is easy, but finding one is hard. Reversibility helps explore the solution space without losing information along the way.
Well, let's be realistic. Real quantum computers still generate heat, don't they? They're not perfectly efficient.
Oh, absolutely. They definitely do. The source acknowledges that current experimental setups still face significant heat generation from all sorts of things: electrical resistance and control wires, imperfect laser cooling, stray particle collisions, the measurement process itself. The point about reversibility relates more to the ideal computational steps themselves, potentially offering a fundamental efficiency gain by avoiding the specific thermodynamic cost of irreversible information erasure at that core level.
Got it. So it's a theoretical advantage that might contribute to efficiency, but not a magic bullet for heat.
Precisely.
Okay, we've covered the fundamental theory, qubits, superposition, entanglement, teleportation, even thermodynamics. But building a physical machine based on these incredibly delicate quantum principles sounds, well, incredibly difficult. The source calls it a $1 million question.
It's arguably a multi-billion-dollar question at this point.
Yeah.
You're right, it's the central challenge: manipulating individual quantum systems, keeping them in their fragile superposition and entangled states long enough to perform a computation.
While shielding them from the environment.
Exactly. Isolating them from all the noise vibrations, stray electromagnetic fields, temperature fluctuations that causes decoherence. It's the core engineering and physics problem. Because of this difficulty, researchers are exploring a whole variety of experimental approaches, using different physical systems as potential qubits.
What are some of these different approaches highlighted in the source? It seems like there are quite a few contenders.
There's quite a diverse list, yeah. Each has its pros and cons. One approach mentioned is using heteropolymers. These are basically custom-designed molecules like linear arrays of atoms where laser pulses could potentially control the quantum states.
Okay, molecules as computers. What else?
A more developed approach is ion traps. Here, you suspend individual charged atoms, ions, and electromagnetic fields in a vacuum.
Trapped ion.
Right. Their internal energy states, and even their collective vibrational modes, can be used as qubits. Lasers are used very precisely to manipulate these states. This approach has been quite successful in demonstrating key quantum operations, including things relevant to algorithms like Shor's, such as quantum Fourier transforms. People like Sirac, Soller, Monroe have done pioneering work here.
Then there's also a quantum electrodynamics, QED, cavity approach mentioned. What's that about?
This involves placing atoms, like cesium atoms, inside a highly reflective cavity, like a tiny mirrored box. Lasers and microwave fields are used to control the interaction between the atoms and individual photons trapped in the cavity. Is a way to create, manipulate, and hopefully preserve superposition and entanglement, as demonstrated by researchers like Turchette mentioned in the source.
And nuclear magnetic resonance, NMR, which seems surprising. Isn't that used in MRI machines for medical imaging?
It is, but the principle can be adapted for quantum computing, though it's a bit different from other approaches. In quantum computing NMR, you typically use a sample of liquid containing a vast number of identical molecules in a powerful NMR machine.
A whole bunch of molecules at once.
Yes, an ensemble. The nuclear spins within these molecules serve as the qubits. You manipulate them collectively using carefully timed radio frequency pulses. The readout, however, is statistical. You measure the average state across the entire ensemble of molecules.
So it's not controlling individual qubits in the same way.
Not usually, which is a key difference and limitation for scaling complex algorithms. But the source notes that NMR achieved some of the earliest experimental demonstrations of quantum algorithms, and makes the interesting claim, perhaps debated now, that this method could tackle certain NP problems in polynomial time due to the ensemble nature.
What about quantum dots? The source seems to give these quite a bit of attention as being promising.
Yes, quantum dots are fascinating. They're tiny semiconductor nanocrystals, sometimes called artificial atoms. They are essentially zero-dimensional systems where electrons are confined in all three spatial directions.
Zero-dimensional, like a point.
Practically, yeah. Very tiny. They're considered promising candidates for qubits, partly because they are solid-state systems and can potentially be controlled electrically, using structures like nanoscale gates, think tiny transistors, to trap and manipulate single electrons within the dot. That electrical control is appealing for integration with existing semiconductor technology.
But they have downsides too.
Definitely. Challenges include difficult readout, actually measuring the state of a single electron spin reliably, and often limited interaction, sometimes only with the nearest neighboring dots, which makes complex circuits hard to design.
And the Kane computer is a specific type of quantum dot system, right?
It is a specific proposal by Bruce Kane. It suggests using the nuclear spin of a single phosphorus atom donor impurity embedded precisely within a silicon crystal lattice as the qubit.
So using the nucleus inside the silicon.
Yes. Control is achieved using a combination of magnetic fields and specific electrodes patterned on the surface, A gates to control the electron near the nucleus, and J gates to control the interaction between neighboring nuclear spins via those electrons. It's a clever hybrid approach, blending ideas from both quantum dots using semiconductor structures and solid-state NMR using nuclear spins.
Okay, one more. The topological quantum computer. That sounds very theoretical and maybe more exotic than the others.
It is quite theoretical still, but the idea is incredibly appealing because it aims to be highly robust against errors. This approach doesn't encode qubits in the state of individual particles like electron spin or photon polarization.
What does it use then?
It proposes encoding quantum information in the collective topological properties of exotic quasi-particles called any's. These are particle-like excitations that can only exist in certain two-dimensional systems, like specific electron gases.
Anyons. And topology.
Right. The computation would involve physically braiding the paths of these anyons around each other in space-time in specific patterns. The quantum information is stored non-locally in the topology of these braids, how they twist and link. The key theoretical advantage is that this topological encoding should be inherently protected against local disturbances. Small bumps or jiggles from the environment shouldn't easily corrupt the stored information because topology is robust against continuous deformation.
That sounds potentially much more error-resistant.
That's the hope, but experimentally realizing and manipulating these anyons and braiding them reliably is still a major frontier research.
Wow. So the sheer variety of these experimental approaches, ions, photons, molecules, spins, dots, topology, it really underscores just how hard this is. Researchers are exploring every promising avenue to find a system that's stable, controllable, and ultimately scalable to thousands or millions of qubits.
Exactly. Each approach has its own strengths and weaknesses in terms of coherence time, how long the quantum state lasts, connectivity between qubits, how easily they can interact, scalability, can you build many of them, and ease of control and measurement. It's a global race, a huge scientific and engineering challenge to identify the most viable path forward.
Since the source delves a bit deeper into the theoretical side of quantum dots, let's spend a moment on the concept of a modified Coulomb potential discussed there. This seems to address a fundamental problem in physics, not just quantum computing.
It does. It relates to a long-standing issue in classical electrodynamics and even its standard quantum version known as the problem of divergences or singularities.
The issue with 1 over r.
Precisely. The standard Coulomb potential, which describes the electrostatic force between charged particles like an electron and a proton, is inversely proportional to the distance, 1r. This means at zero distance, r is 0, the potential mathematically goes to infinity.
Which isn't physically realistic.
Right. This singularity leads to non-physical infinite values when calculating things like the self-energy of a point charge. While quantum field theory has sophisticated techniques like renormalization to handle some infinities, this basic singularity at very small scales persists and becomes particularly relevant when you're dealing with particles tightly confined in systems like nanomaterials or, indeed, quantum dots. The standard potential might just break down.
So the standard potential isn't sufficient to accurately describe interactions within something like a quantum dot at the smallest distances. We need something better.
It seems likely inadequate at those scales, yeah. The source introduces theoretical work referencing a formalism proposed by Professor Y.M. Gupta that attempts to resolve this. The idea is to develop a potential function that is regular, meaning it stays finite and well-behaved at the origin, or anywhere else, while still being fully consistent with Maxwell's equations, the fundamental laws of electromagnetism.
So fix the potential without breaking the underlying physics laws. What does this modified potential look like for something like a quantum dot?
The proposed potential has an interesting structure. It essentially transitions its mathematical form at a certain critical radius, which the source links conceptually to the Compton wavelength of the confined particle.
It changes shape.
Yes. For distances less than this critical radius, or RRC, the potential is described as V equals half khr v t. You might recognize that R dependence.
That looks like the potential for a spring. a simple harmonic oscillator.
Exactly. It's a harmonic oscillator, potential parabolic, like a bowl, getting stronger quadratically as you move away from the center. Then, for distances greater than this critical radius, RAC, it smoothly transitions back to the familiar standard Coulomb potential, V equals 1 dimensional 1,4.
Okay, so harmonic inside, Coulomb outside. And a critical radius RT is related to the Compton wavelength. What is that exactly again?
The Compton wavelength is a fundamental length scale associated with a particle related to its mass, Planck's constant h, and the speed of light. It represents a scale where quantum effects and relativity become really important for that particle. For an electron, it's incredibly tiny, about 2.4 picometers.
But for quantum dots, the relevant scale is larger.
Yes, the source suggests that the effective critical radius RC, where the potential form changes inside a quantum dot, is likely larger, perhaps in the range of 10 to 100 nanometers, and is determined more by the physical size of the dot and the strong confinement effects rather than the bare Compton wavelength itself. It's a characteristic scale of the nanosystem.
What's the intuition behind the potential changing forms? Why would it become harmonic, like a spring, at tiny distances inside the dot?
Well, the source offers an analogy. Think about trying to move through a very congested street with high walls on either side. At the nanoscale, within the tight confines of a quantum dot, the effective potential felt by an electron isn't just the simple attraction to a positive charge. It's also strongly influenced by the hard boundaries, repulsion from other electrons, and the complex interactions within that severely confined space. This combined effect, this sort of quantum congestion, might effectively create a potential, well, that near its center looks more like a smooth harmonic oscillator bowl than the sharp cusp of the 1 potential. It's a way to model the strong confinement.
So you can then use this modified potential in the main equation of quantum mechanics.
Exactly. You can plug this two-part potential into the Schrödinger wave equation, the fundamental equation describing how a quantum system evolves for a particle, like an electron, trapped within the quantum dot. You essentially treat it like a quantum version of the hydrogen atom problem, a two-body bound state, but using this modified potential instead of the pure Coulomb one.
And you need to make sure the solution is smooth at the boundary.
Yes, a key part of solving it is applying boundary conditions. The wave function describing the electron and its derivative must be smooth and continuous at that critical radius arc, where the potential form changes from harmonic to Coulombic.
The source includes numerical results and plots based on solving this equation in its annexure section. What do they show?
They do. The analysis finds that for specific sizes of quantum dots and specific quantum states, defined by quantum numbers like the angular momentum quantum number L, only certain discrete, stable energy levels or eigenvalues are possible solutions. The plots visually show where the calculated wave functions correctly match the boundary conditions, identifying these allowed stable energy values, labeled B in the tables.
And what's the key takeaway from this theoretical exercise for quantum dots?
A key insight highlighted in the source, based on this theoretical work, is that if the calculated wave function for an electron state shows that the electron is mostly confined within this critical radius RT, where the potential is harmonic, then that quantum dot configuration is likely to be particularly stable. The harmonic nature of the potential in that region helps trap the electron effectively.
So the theory suggests these dots can be stable containers for quantum states. And there was speculation about this harmonic nature being deeper.
Yes, the source muses a bit on this, suggesting that this apparent harmonic nature of the effective potential at short distances inside the dot might hint at a more fundamental harmonic character of nature itself at the quantum scale. It even speculates this could be related to the origin of the Heisenberg uncertainty principle, perhaps arising from inherent fluctuations within such a fundamental harmonic potential. That's pretty deep speculation, but an interesting thought prompted by the model.
The source also briefly mentions analyzing quantum wires using this same modified potential approach.
Right. Quantum wires are essentially one-dimensional systems confined in 2 dimensions but long in the third. Applying this modified potential formalism to model a quantum wire yields a result that makes intuitive sense. The part of the wave function describing the particle's motion along the length of the wire, the z's direction in their example, turns out to be the wave function of a free particle.
Because it's free to move in that direction.
Exactly. It's confined radially, where the modified potential matters, but free to propagate along the wire's axis. The analysis shows the Compton wavelength scale still plays a fundamental role in determining the properties in the confined dimensions there as well.
So this theoretical analysis, using a modified potential to get sensible, stable solutions, helps bolster the case for quantum dots being promising candidates for building qubits.
Yes, it provides theoretical support for their potential stability and suitability.
And the source grounds this theory in reality by mentioning a visit to a nanotechnology lab. Seeing the actual tech must make a difference.
Absolutely. That section describing the lab visit really helps connect the abstract physics to tangible technology. Seeing instruments like the atomic force microscope, AFM, in action figure 11, apparently shows an AFM image of quantum dots, and figure 13 has related data plots and the scanning tunneling microscope, STM.
Which itself relies on quantum tunneling, right? Figure 12 shows the tip.
Exactly. The STM works based on electrons quantum tunneling across a tiny gap, another purely quantum effect. Seeing how these nanomaterials are actually fabricated, maybe using methods like the wet chemical synthesis mentioned, it makes it real. It reinforces that whole idea of diminishing dimensions discussed in the source, going from 3D bulk materials down to 2D quantum wells, then 1D quantum wires, and finally 0D quantum dots, and how drastically the physics changes with that increasing confinement.
And the modified potential analysis supports the idea that this zero-D confinement in quantum dots could lead to low decoherence, making them potentially stable platforms for qubits.
That seems to be the conclusion drawn, yes. The strong confinement, possibly described by that harmonic-like potential well, might help isolate the qubit state.
Okay, so we've explored the incredible potential and the fascinating theoretical and experimental efforts, but let's pivot to the major roadblocks. What are the really big challenges and open questions that need to be solved to make large-scale, useful quantum computing a reality?
Well, the single biggest challenge, the absolute elephant in the room for pretty much every single experimental approach, is decoherence.
The fragility problem.
Exactly. Quantum superpositions and entanglement are incredibly delicate. They're easily destroyed. Any unintended interaction with the surrounding environment, a stray electromagnetic field, a tiny vibration, thermal energy from heat, anything can cause the quantum state to lose its coherence, its quantumness, and collapse into a boring old classical state
It's like trying to keep that spinning coin perfectly balanced.
in the middle of a hurricane.
Yeah.
Keeping a quantum system sufficiently isolated and coherent for long enough to perform a complex computation is just monumentally difficult. We're talking fractions of a second, sometimes much less, before the quantum state decays.
And then there's the deep mystery we touched on earlier, the measurement problem. It's not just a practical issue, but a conceptual one.
Yes, it's arguably one of the deepest unresolved issues in the foundations of quantum mechanics. The standard theory describes the smooth, continuous, reversible evolution of a quantum system using the Schrödinger equation, unitary evolution. But then, the act of measurement or observation seems to abruptly and instantaneously force the system out of its superposition or entangled state into a single, definite classical outcome.
The wave function collapse.
Right, and this collapse process feels fundamentally different. It's probabilistic, it's irreversible, and it's not really described by the Schrödinger equation itself. It's like an extra rule tacked onto the theory. How and why does this happen? It seems tied to the uncertainty principle, limiting what we can simultaneously know, but the mechanism is debated.
The source looks at some alternative ways to think about or interpret this measurement problem, doesn't it?
It does. One angle suggested is looking at it through the lens of irreversibility and thermodynamics. Measurement inevitably involves the quantum system interacting with a much larger measuring apparatus, which is part of the environment. This interaction involves energy exchange and is inherently an irreversible process, much like the second law of thermodynamics describes how entropy disorder always increases in irreversible processes. Maybe the apparent collapse is just a manifestation of this fundamental thermodynamic irreversibility kicking in.
Interesting. And what about the symmetry breaking idea?
That's another fascinating perspective presented in the source. It suggests explaining the measurement collapse through the concept of symmetry breaking, a common idea in physics, where a system transitions into a state that has less symmetry than the underlying physical laws governing it.
How does that apply here?
Well, a superposition state, like 0 plus 1, is often symmetric in some sense, but the outcome of a measurement, either 0 or 1, is asymmetric. A choice has been made. The source references philosophical principles like Leibniz's principle of sufficient reason, basically. An asymmetric outcome must have a reason, a cause for the symmetry breaking, and Curie's principle, which relates the symmetries of causes and effects.
So the question becomes, what causes the symmetry to break during measurement?
Exactly. What is the specific symmetry that gets broken? Is it a local process happening right at the system, or something more global involving the observer and environment? The source proposes this as a crucial area for future research, suggesting that understanding this symmetry breaking could potentially provide a deeper understanding of why the uncertainty principle exists in the first place. Maybe uncertainty is a consequence of how measurement breaks symmetry.
And the quantum no-cloning theorem, the rule that you can't perfectly copy an unknown quantum state, is also related to this irreversibility. It's not just about uncertainty.
The source connects those ideas too. While the no-cloning theorem is often explained simply by saying that measurement disturbs the state due to the uncertainty principle, you can also view it as a consequence of the fundamental irreversibility introduced by any process attempting observation or copying. The very act of trying to extract enough information to make a perfect clone involves irreversible interactions, energy exchange, and entropy increase, making a perfect reversible copy impossible.
Okay, circling back to entanglement, the source mentioned different mathematical ways to describe these EPR correlations, these spooky connections.
Yes, it touches on two main strategies you might try if you want to incorporate these strong correlations directly into the quantum description. One way is to modify the system's Hamiltonian, that's the mathematical operator, representing its total energy and dynamics. You could try adding specific potential energy terms that explicitly represent the interaction or correlation between the entangled particles.
So build the correlation into the energy landscape.
Right. The other approach mentioned is to modify the wave function itself. Instead of just summing up basis states, you might try to build a correlation term directly into the structure of the wave function, like the delta term attempted in Chapter 3 of the source material, Caesar's, Besant, and Pratt.
And thinking about the wave function and correlation leads to categorizing quantum states based on how entangled they are. This seemed important for computation.
It does. And the source draws some interesting distinctions based on the degree of correlation or entanglement present in a state, which have implications for how useful that state is for different quantum tasks.
Okay, what are the categories?
First, you have purely unentangled states. The source defines these as having correlation equals 0. These are states where the wave function of multi-qubit system can be written simply as a product, or maybe a sum, of the individual qubit states. They behave independently.
And these are good for?
The source states these are the states suitable for running efficient quantum algorithms and allow for vast information storage. It links this conceptually to representations like the Bloch sphere, which describes the state of a single unentangled qubit. This is where you can define and manipulate individual qubit information easily.
Makes sense. What's next?
Second, there are mixed entangled states, where the correlation is somewhere between 0 and 1, 0 correlation 1. These states are messy. They contain a mixture of entangled components and unentangled components all jumbled together.
And these are less useful.
According to the source, yes, it makes a critical point. These mixed states are deemed not fit for computational purposes. Why? Because the entangled and unentangled parts are intrinsically mixed. You can't effectively isolate and use the entanglement reliably for computation without inadvertently disturbing or collapsing the state in unwanted ways, which introduces errors. They're hard to control precisely.
Okay, so avoid the messy middle. What's the third type?
Third, you have purely entangled states, where correlation equals 1. These are states, like the ideal EPR pairs, whose description is entirely defined by the correlation between the parts. There's no independent information in the individual qubits, only shared information.
And what are these good for?
The source says these purely entangled states are ideal for transporting quantum information, like in quantum teleportation, where the EPR pair acts as the channel. But, and this is important, they are not suitable for general information storage or for performing arbitrary computations themselves. You can't easily encode or manipulate information onto a purely entangled state in the way needed for running most algorithms. The information isn't locally accessible.
So, unentangled for storage and algorithms, purely entangled for communication, and mixed states are problematic.
That seems to be the perspective presented. Understanding and being able to create, manipulate, and characterize these different types of states, especially dealing with the complex entanglement in many qubit systems, is absolutely crucial for building functional quantum computers with robust logic gates and effective error correction schemes. Error correction, in particular, needs to handle the correlated errors that entanglement can cause.
So, the challenges are significant. Taming decoherence, resolving the measurement mystery, precisely creating and controlling these different kinds of entanglement. But the potential benefits, as we've discussed, are enormous. Looking ahead, What does the future hold for this field, and what are the really profound implications we should keep in mind?
Well, the foundations are certainly established, the basic principles are understood, but the field is definitely still in its growth phase. It's maybe analogous to classical computing in the 1950s or 60s. Future progress really requires continued exploration and breakthroughs across multiple fronts simultaneously.
Like what?
We need new and more efficient quantum algorithms tailored for problems beyond just factoring and search. We desperately need better ways to control decoherence and extend coherence times, making qubits stay quantum for longer. We need major technological breakthroughs in actually building, connecting, and scaling these devices reliably from tens of qubits to perhaps millions. And we need to keep identifying the specific applications where quantum computers will provide a real practical advantage over classical ones.
Beyond factoring and searching, what are some of the potential applications that excite researchers, according to the source?
As the source notes, quantum computers could be powerful tools for tackling other computationally hard problems. Their inherent reversibility makes them potentially well-suited for solving certain NP-complete problems, which are notoriously difficult classically.
What else?
Their ability to naturally leverage quantum interference waves canceling or reinforcing could be applied to global optimization problems, like finding the absolute lowest point in a very complex energy landscape with many valleys.
Yeah.
And quantum tunneling, that ability for a particle to pass through an energy barrier it classically shouldn't be able to overcome,
Yeah.
that could potentially enhance techniques like simulated annealing, which are used in optimization and machine learning. And of course, two huge potential areas are simulating complex molecules for drug discovery and designing novel materials with specific quantum properties, areas where classical simulation hits that exponential wall very quickly.
It sounds like new theoretical tools might be needed as well, not just experimental ones.
The source suggests so, yes. It mentions potentially leveraging the mathematical properties of complex numbers more deeply in quantum algorithms. It also points towards extending our theoretical framework more fully into quantum field theory, QFT.
QFT, how is that relevant?
QFT is the framework that describes the creation and destruction of quantum metal particles or energy excitations. This is directly relevant in many experimental platforms, like those using photons in quantum optics. The source even intriguingly suggests that the famous double-slit experiment showing wave-particle duality could perhaps be reinterpreted within QFT as a kind of fundamental copy operation of quantum field states. And, as we just discussed, improving our characterization and mathematical understanding of complex, many-body entanglement is absolutely vital. We need better tools to describe and quantify entanglement in large systems, which is essential for developing more robust quantum gates and designing sophisticated error correction codes that can handle the unique types of correlated errors that quantum systems experience.
And the quest to control decoherence will continue to be absolutely central, won't it?
Oh, undoubtedly. That remains arguably the major roadblock. We need a much deeper understanding of the detailed dynamics of how quantum systems interact with their specific environments. Perhaps we can find clever ways to engineer the environment or identify specific quantum states, sometimes called pointer states, or decoherence-free subspaces that are naturally more stable or favored and less susceptible to disruption within certain experimental setups. Anything to push those coherence times longer.
This whole journey into manipulating and controlling the quantum world, dealing with measurement, it seems to highlight a need for a more unified theoretical picture, doesn't it?
It really does. There's a sense that our current framework is maybe incomplete or at least awkwardly split. Ultimately, both the quantum system we're trying to compute with and the classical observer or measuring device are, at a fundamental level, made of quantum stuff governed by quantum rules.
Right.
Yet the standard description of measurement treats the collapse as something special, something outside the smooth, reversible, unitary evolution described by the main quantum equations. There's a strong desire, a long-standing quest, for a single, unified quantum theory that can seamlessly describe both the microscopic system and the macroscopic observer, encompassing both the unitary evolution and the measurement process and decoherence within one consistent framework.
What would that achieve?
Well, besides resolving deep conceptual puzzles, such a theory could potentially lead to practical benefits, like designing much better quantum detectors. It could also help us truly understand the fuzzy boundary, the quantum to classical transition, where the weird microscopic quantum world somehow morphs into the familiar macroscopic classical world we experience. How does that happen?
And by pushing these boundaries, by really trying to control these delicate quantum effects, the source even suggests we might stumble upon something entirely new, perhaps even a third paradigm beyond classical and quantum physics. That sounds radical.
That's definitely one of the most provocative and forward-looking thoughts presented in the source material. Think about the historical progression of physics in information.
Okay.
Classical mechanics gave us determinism. In principle, if you knew the initial position and momentum of everything, you could predict the future perfectly. Both position x and momentum p could be measured to any desired accuracy simultaneously.
Got it. Deterministic world.
Then quantum mechanics came along and introduced limited indeterminism. The uncertainty principle says there's a fundamental limit. You can know either position x or momentum p precisely, but you cannot know both simultaneously with arbitrary accuracy. There's an inherent fuzziness.
Okay, limited uncertainty. So what would a potential third paradigm look like?
The idea speculated upon in the source is complete indeterminism. This is a hypothetical state of affairs where, perhaps at some deeper level or under certain conditions, neither position x nor momentum p, to any degree of accuracy, can be measured.
Neither. Not even one of them accurately.
That's the speculation. It's a highly theoretical concept, suggesting a reality where our ability to even define or measure these fundamental properties might be limited in ways we currently can't grasp. If such a regime exists, quantum mechanics as we know it, with its limited indeterminism, might just be a special, approximate case of this deeper, completely indeterminate reality.
That's hard to wrap your head around. What would that even mean?
It would require completely new definitions for fundamental concepts, maybe even rethinking the Schrödinger equation and the uncertainty principle itself.
And the source connects this extreme idea of complete indeterminism to the notoriously difficult concept of the consciousness of the observer, even mentioning Stephen Hawking's interest in this area.
Yes, it briefly notes that the role, if any, of the observer's consciousness in the quantum measurement process is still a fringe but active area of research and philosophical debate. This speculative notion of ultimate indeterminism is linked in the source to that profoundly difficult, perhaps unanswerable question about the connection between mind and physical reality.
Wow, it's definitely mind-bending stuff. It really reminds you how much we still don't understand about reality at its deepest levels.
Absolutely. Quantum mechanics constantly challenges our everyday intuition, and exploring its frontiers, like in quantum computing, pushes those challenges even further.
So to try and bring it all together then, what are the key takeaways for someone listening to this deep dive into the basics of quantum computing based on the source material we've unpacked?
Okay, well, we've seen that classical computers, despite their incredible power, face fundamental limits. They're hitting physical size constraints as we approach the atomic scale, and they're limited by their inherently serial way of processing information based on classical bits, 0 or 1.
Right, the classical walls.
Quantum computing offers a revolutionary alternative by not fighting, but harnessing the weird rules of quantum mechanics. Phenomena like superposition, allowing qubits to be 0, 1, or both at once, and entanglement, that spooky non-local connection between qubits, are the key resources.
And these resources enable new possibilities.
They enable powerful concepts like quantum parallelism, exploring many possibilities simultaneously within the quantum state, and quantum teleportation, moving quantum information using entanglement. These capabilities promise exponential speedups for certain critical problems, most famously factoring large numbers, which could break current cryptography, but also potentially for search, optimization, and simulation.
We've looked at the incredible experimental efforts underway, this diverse zoo of approaches, trapped ions, superconducting circuits, though maybe not detailed here, photons, NMR, quantum dots, even topology, all trying to build stable, scalable qubits. And we touched on some deep theoretical work, like trying to better model the physics inside quantum dots using modified potentials.
But we've also squarely faced the enormous challenges.
Yeah.
The biggest practical hurdle is decoherence. The extreme fragility of quantum states, how easily they get disrupted by the environment. And then there are the profound, unresolved conceptual mysteries surrounding the quantum measurement problem. Why does measuring cause a collapse? And the precise nature and control of complex entanglement.
So the implications are vast, aren't they? Reaching way beyond just faster computation.
Definitely. It impacts our fundamental understanding of physics itself. It could revolutionize fields like cryptography, drug discovery, material science, maybe even AI. And it forces us to confront these deep questions about the nature of reality, the role of information, the process of measurement, and maybe even, as the source speculates, the limits of determinism and the role of consciousness. This deep dive has really aimed to give you the core nuggets, the essential concepts, the key players, the challenges, and the exciting potential drawn from the source material to get you well informed on this rapidly evolving and frankly mind-bending field.
As the source concludes, the future isn't entirely clear, the exact path forward is uncertain, but it is undeniably promising. The whole endeavor is really about shifting our relationship with the quantum world, moving from simply observing its strange effects to actively mastering and controlling them for practical use.
Precisely. It's about engineering the quantum.
And that leaves us with that final, provocative thought to chew on. Are we just on the cusp of a monumental technological leap that will reshape industries and solve intractable problems? Or, by pushing the boundaries of physics this hard, are we perhaps bumping up against the limits of quantum mechanics itself, maybe even uncovering hints of an entirely new understanding of reality, the potential third paradigm beyond both classical and quantum mechanics? What new questions does grappling with all this quantum weirdness spark for you?